Hello everybody, it's Tobi Delbruck here. I'm going to tell you about Misha Mahowald's beautiful stereo chip. So around the time when I started out in Carver Mead's lab, Misha Mahowald was already there, and everybody was being taught by Christoph Koch, Dave Van Essen, John Allman, people like that, the neuroscience, and we were all reading this book called Vision by David Marr. Or you can say David Marr died of cancer in his 40s, but we all thought this book was very cool. And so I'm going to tell you about some ideas that came out of that book that influenced the way that we worked on stereo. So take a look at this stereo picture here taken from the house in Pasadena with my mother Manny. It's actually a stereo picture. The differences between the left and right half of this picture are very, very subtle. You can barely see them. But if you look carefully, you'll see, like for example, that there's a slight difference in the overlap of the head with the background, and if you look very, very carefully, you'll see that there's a slight difference. For example, it's really quite hard to see, but in the alignment of foreground and background between the two pictures. But trust me that if you view this stereo pair uncrossed, in other words, with your eyes looking straight ahead, and I'll turn off the video here in a minute, if you just view it straight ahead, especially if you need to make it small like this, so that it's not too far apart. It needs to be about as far apart as your two eyes, and especially it helps if you're nearsighted. So then you can take off your glasses and then get close to the picture, and your brain still thinks that it's looking at something far away, because there's a strong coupling between the vergence and the accommodation, or vergence and focus of the eyes. So if you can now get close to this screen, and it has to be quite small actually. So remember, just take your eye distance and scale it so that it's about that far apart. If you fuse those two pictures together, just trust me when I tell you, a very powerful impression of depth will come out. Many will stand out from the background, and you'll see a very strong impression that there's kind of depth in the scene. And this has been used for a long, long time to bring pictures to life, like landscape pictures and stuff like that. And I've taken lots of these stereo pictures. I found it endlessly fascinating. The impression is just so powerful. It brings such depth to the picture. But for a long, long time, before the 1970s, people thought that stereo vision in the brain was strongly driven by recognizing stuff in a picture, and the fact that there was, known stuff. You kind of knew that something was in the foreground and the background. Of course, that's a very powerful cue. But then along came Bela Julesz, who I had a chance to meet as a very beginning PhD student. And in 1971, he published this very cool book where he summarized some experiments he had done. The book is called Foundations of Cyclopean Perception. It's a cool book with stereo glasses and lots of stereograms to enjoy. But in particular, he introduced the idea of this random dot stereogram. I'm sure many people have heard of this, but it consists of a pair of images like this. And if you fuse this pair of images, and again, you should do it uncrossed. And in Bela's book, they're presented as red and green pair. And you have these glasses that only let the red part of the picture through the right eye and the green part through the left eye, or vice versa. But anyway, if you fuse these two pictures, what do you think you would see? You can inspect these to death and you won't see anything. Have you seen it before? Well, this particular example has random dot bars standing out in front of the background. In fact, if I take this picture and scale it down to the interocular distance and look at it, I can see that these little bars right here, I can see them standing out about this far from the page, and like half a centimeter from the page at a viewing distance of maybe 30 centimeters. And that's because there are little shifts of this random patterns, between the left and right eye to cause disparity between the two eyes that the brain interprets as a depth cue. Anyhow, this had a big influence on the whole field because now people understood that the brain could do it without understanding anything about the structure of the thing. It was really doing low-level matching and depth extraction. And the cues are really powerful. So that fascinated us. And so that led to the development of the first neuromorphic kind of stereo vision chip. And you can see that, let me just talk about the problem of stereopsis at all. This is really for beginners, so skip it if you want. But here you have I guess it's a right eye and a left eye looking down on it. And here this represents planes of distance in the scene, and this represents some points on the left eye and the right eye. Now consider what happens if the two eyes each see, the left eye sees 4 orange dots floating in black space. Okay, so there's nothing else around. So the left eye sees these orange dots, and the right eye sees the same orange dots. So how does the brain interpret that, or how should we interpret that as a 3D thing out there in the world? Well, one obvious interpretation is that they lie on a plane like this, right? You can't tell the difference between dots in the two eyes, so one interpretation is like that, right? But an equally valid interpretation is that you're actually seeing something that looks like what? Like that, right? Because that would produce exactly the same retinal image in both eyes. Okay. But usually you interpret the flat frontal parallel plane because it's more common. But yeah, that's an equally valid interpretation. But now consider this situation here. So you see here, it's the same impression on the two eyes. Now consider this impression. And I'm leading up to something because it leads up to the Marr-Poggio algorithm for stereo vision that we first implemented. Now think about this. The left eye sees 2 orange dots like this, and then one displaced this way to the right. Now the right eye sees these orange dots, right? Now there's no displacement. In other words, there's a disparity, a so-called disparity between these 2 dots here. These 2 are kind of lined up at the average distance, and these guys have a different shift in the 2 eyes. This relative shift in the 2 eyes is called disparity. There's a mathematical definition, but don't worry about that right now. You'll see what it means geometrically later on the stereo chips. Okay, so now how do you interpret this? Well, what could cause this particular pair of retinal, simulations? Okay, that could do it, right? Because now the left eye sees these 2 dots here, and then because this one's a bit further away, it's shifted to the right. On the other hand, on the right eye, you see the same 2 dots here, but now because of the fact that it's further away and you're looking at it from this angle, it's actually shifted closer, right? You can see the angle is smaller here. Here, for the left eye, the angle is bigger, and for the right eye, the angle is smaller. So that's a possible interpretation of this thing in depth. 2 points sitting like that and one further away. There are possibly other interpretations. Anyhow, David Marr and Tomi Poggio thought about this, and they said, look, let's think about this as a kind of a cooperative and competitive process of deciding how the dots should match up, how the features should match up. So here's how this Marr-Poggio algorithm works. It's one of the first collective neural networks, with feedback and stuff, I believe, and it's cool because it didn't have practical implication for stereo vision, but it had a big influence on the whole field, I think. So you take the same eyes now and lay them out on the left axis and the right axis. And now when there's a feature on the left eye, now you have one-dimensional eyes, by the way. So you have features here, and you also have features here. And now you can make an area here which represents the possible matches between the 2 things. And then if you go in this direction, so you have, like I say, a feature on the left eye, feature on the right eye, and where they cross, here you have a match, right? And now, so you call that zero disparity. It's kind of arbitrary in some way, but if you had 2 sensors, it might be the middle of the 2 sensors. So you call one relative displacement between the 2 eyes zero disparity, and all the places that are zero disparity are represented by this yellow line. Now you can add more planes here to the side on the diagonals from this first one, and these represent disparity between the 2 eyes. For example, this line here represents matches between the right eye and left eye, where the left eye is shifted, I think, is it 1 pixel to the right? I think it's 1 pixel to the right and 2 pixels to the right, and so on. Okay, so once you do that, now you can introduce actually a physical mechanism for resolving these possible false matches between the 2 eyes, and some notion of smoothness in space, which typifies the real world. And the way they did it is by introducing competition along the lines of sight with winner-take-alls, and cooperation along disparity planes. So you say, look, let's try to resolve these false matches, these possible false matches, by encouraging matches along disparity planes, but not allowing multiple matches along any one line of sight. And so, so this is a cool idea. So how does it actually work in practice? I'll turn off my camera now. I hope I can. Okay, I don't know if I can. Anyhow, so Carver, I came to Carver's lab, and the very first thing he asked me to work on was a disparity chip, because he'd heard about this algorithm. And so we went to the Athenaeum, and then he sketched out on a napkin the idea for the disparity chip. So I was already working on silicon photoreceptors and stuff. So you take two one-dimensional retinas on a chip, you just lay them out next to each other. It's much more compact if you lay them next to each other than crossing them. And then you can show things to the retina by just projecting patterns onto the two eyes, as you'll see later. But anyway, you take these two retinas here, and now you just draw wires connecting them like this. And anytime the wires cross like this, you put some correlation unit, something that computes the correlation or the sameness, the similarity between the two eyes features. And then you draw wires this direction here, and you just add up those correlations. Right? So if the two eyes are lined up perfectly, then the maximum correlation will be on this middle wire here. But say the top retina is shifted to the right, then the maximum correlation would be along this row. I hope that's clear. Okay, so that was my very first chip actually in Carver's lab, was to send out a chip like that. And I have a great story about Moses regarding that. So that solves just the global shift between the two eyes. Doesn't solve the matching problem or anything, but you can just compute the relative shift between the two eyes. Might be useful for something like in autofocus mechanism. Okay, so that introduced the Marr chip architecture that then Misha and I started working on. The very first Marr chip architecture. Again, you have the right eye input down here, the left eye input up here, and now you introduce cooperation along these lines, along these disparity planes by using resistive network to couple the pixels together. You have a unit that computes the correlation between the features, and now you introduce something just a tilt in the line. So the top eye's correlation line goes like this, and then it goes down, and the bottom one goes like this, and then it goes here. And so now these wires, when they cross, they represent the correlations between the shift between the left and right eye in a slightly different way. And now you can introduce competition by putting winner-take-alls along these orange and green lines. All right. So actually, when you take the whole chip and assemble the array of pixels, it turns in the whole array of stuff. It just turned into a chip architecture that looks like this. You have a retina, 1D retina here, 1D retina here. You have all your pixel circuits here that do the cooperation with resistive network, competition with winner-take-alls, and then you just read out the whole thing with the scanner, 2D scanner, 2D video scanner, so you can just display the output of the thing right on a multi-sync monitor. And so that's what one of the chips looks like. You can see the retinas at the bottom and the top. It really had a very small number of pads. All the biases were brought in for potentiometers, and it was cool. I mean, it had a built-in video scanner, so it would just directly generate video. So what does it actually look like, the output? So now you take a pattern and project it onto the chip. And here, the pattern is just a set of black and white bars. So in this part of the image right here, there's no disparity, right? The images are lined up on the left and right eye. On this part of the pattern here, you introduce a disparity by making tilted bars. So now the top retina's features are shifted to the right relative to the bottom retina. And if you look at the retinal outputs as a function of pixel number, this is just relative retinal output in volts, I think. These are just static log photoreceptors. Here you can see there's no disparity between the top retina and the bottom retina in the dashed and solid curves. And then you get to the right part, there's significant disparity. And you can see the patterns on the retinas here and here too. And now when you look at the correlation computed by the chip without turning on any of the competition or the resistive network, the raw correlation says that, yeah, there's a correlation between these features, right? And I'll tell you later how the correlation is computed, but basically it's just, you can see the raw correlation, but now you turn on the winner-take-all circuits and the resistive network, and bammo, it settles down to this plane here, which is zero disparity, and this plane up here at the cross disparity. The disparity where the top right is shifted to the right. Because remember, the lines go up and then they shift over like that. That's pretty cool. The other stuff is still there, but it's basically strongly suppressed. And now I can play you, the Marr chip is actually a rare video of this Marr Poggio chip in action around 1989. And you can read about the work. It's published here in this book chapter, which is available online. So the chip is right here, right? You can see it's a Moses chip, I think 3 micron technology. You just take the cover off, and now with a microscope lens or with a, just a lens, you just drop a lens on top, and then you can wave patterns around by hand above it. And this is what it looks like. Well, there's the lens. So you can see the disparity planes. It's much too fast, but if you see here, if you just pause this video briefly, and I created a pattern there where you had a bump, a little bit like that random dot stereogram I showed you from Bela Julesz, this thing standing out from the background. And it really just worked. You could see this thing working. It was quite a cool feeling to see it work especially back then. Okay, so Misha was not satisfied with this Marr Poggio. All this is leading up to what Misha did, right? The cool stuff that Misha did. She wasn't satisfied with that. Why? Okay, it only dealt with frontoparallel planes, and in the real world, you can easily match tilted surfaces and all kind of complex stuff. So, this frontoparallel plane, which is forced by this resistive network running along the disparity lines, doesn't make sense. Also, it fills in the solution even when there's no features. So it didn't seem very sensible. I mean, you shouldn't really fill in when there's no features at all. It's not based on spikes or spike timing. And there's particularly what bothered her, there's no analogs of cortical disparity tuned cells, because we were listening to what the neuroscience said, and I'll tell you about that. So there's a fellow named Gian Poggio, and actually this is the brother of Tommy Poggio. So this is like the Italian family. One of them went into AI and founded the MIT AI lab and trained people like the guy who's heading Google DeepMind and had a huge influence on that. And the brother, slightly older brother, I think, Gian Poggio, went into neuroscience, and he had a huge influence on the biology of binocular vision because he was the first one to carefully measure and characterize the responses of these cortical cells to binocular stimuli. And what he would do would show binocular stimuli in a classic paralyzed animal, I think it was cat or monkey or macaque, and record the responses of these disparity tuned cells. And so here's a disparity. I think it's in degrees, but I'm not sure about that. And here the spike raster response is a function of time. But basically the point is that there are a class of cells which are tuned to nearly zero disparity. So they're like tuned to features that are right on the plane of fixation. But there's another, and he called these tuned excitatory cells. Not all of them are tuned right at the plane of fixation. He also found cells that are tuned off the plane of fixation, but also sharply tuned to a particular disparity. Tend to get more broadly tuned as you go away from the plane of fixation. And not only were there tuned excitatory cells like this that seem to compute. So in this cool recording here, it actually shows from 1965, Thorsten Wiesel and David Hubel binocular recordings from macaque visual cortex area V1. Here they're showing a visual stimulus moving around, and they're showing that this is an on-center cell, a sustained on-center cell. And now Thorsten is showing a bar going back and forth and moving the distance closer and further. Now listen carefully. Responding less strongly. He's getting closer and closer. And now he's going to move further away again. Listen. Really strong there. now weaker again. So this is quite a cool thing because it shows that this is a disparity-tuned simple cell. It's not direction selective, it's rather broadly tuned for disparity. See, it's hardly responding at all after. And now I hope this gives some impression of the kind of responses that people really get from such neurons. Correlation. There are also a big class of cells called near and far cells that a little peak at a particular disparity, but mostly they responded to a feature that was further away than the plane of fixation or closer than the plane of fixation. So they seem to say that stuff was further away than where you're looking at or closer, but not sharply tuned to a particular disparity. And there were disparity flat cells. These are interesting cells that would respond to one eye only. Well, let's see now. You have to be careful about this. They have a very flat response to disparity. These are all spike rasters here at different disparities between the left and right eye. And if you show it to the left eye or the right eye, you get the same response. So it's actually a binocular cell, right? It responds to both eyes, but there's no difference if you show it to both eyes. So it's kind of has a flat response. And you had two inhibitory neurons that respond to the left eye, the right eye, but if you showed it to both eyes, it would respond weaker. And here's another example. You show it to the right eye, and the left eye, if you show it to both eyes or the left eye, it actually inhibits the response to the right eye. And okay, so that led to Misha coming up with her stereo chip architecture, which actually incorporated all these classes of neurons and very cool, mixture of representation between place and value encodings and feedback, which I'm going to tell you about now. So she started out with the same basic architecture of cyclopean pixels, where this direction here represents the angle of view, and these lines here correlate with correlator units. They correlate the features from the left and right retina. And then you take another one of those and you put it next to that and so on. And now you put correlator units here. And now here comes Misha's magic sauce. You take the same correlator unit that correlates between left and right eyes, and now you broadcast across the chip a disparity reference signal. This is an analog voltage that starts at 0 volts here and goes to VDD volts on the other side of the chip. It's just broadcast to all the pixels by wires that go in this direction. So every pixel in this correlator array has access to this so-called disparity reference analog voltage signal. And you take that voltage and send it into a buffer, a unity gain transconductance amplifier buffer, but you bias the conductance of that transconductance with the correlation. So at every location here, every correlation drives some weighted value of this disparity reference out. Okay, now you collect all those values together along a cyclopean direction and call that the analog disparity value. Every correlation here votes for a particular disparity reference value based on the correlation, and then they average it together with this follower aggregation on this analog disparity value wire. So now this wire represents the analog disparity in the cyclopean pixel. Okay, doesn't stop there. Next step is you take that analog disparity value back in and you ask at every pixel, how similar is my disparity to that analog disparity value? And you compute that with a bump circuit, which is a circuit that I came up with when I was working on autofocus actually. But you now compute the similarity of this analog disparity value with what you think your disparity is right here in this cyclopean pixel, right? And you feed that also back in to this computation. I'll tell you more about that in the circuit in a moment. So now it becomes a kind of feedback circuit. It's not just feed forward like computing the correlation and weighting it together to compute a disparity, but you take your own notion of what your disparity is and you feed how much you agree with that and use that to feed back in again to the computation. And then the next thing you do and that's shown here, right? That's added together with the actual correlation. You add those two things together and compute the analog disparity value. Next thing that happens is you now need to enforce like somehow smoothness of disparity in space, right? Not necessarily flat frontal parallel, but it needs to be smooth until you break it somewhere. And you do that now by taking this analog disparity value and now smoothing it across cyclopean angle of view using a resistive network, right? So you take all these guys here, and then they get averaged together with neighboring cyclopean pixels. That enforces smooth disparity. Okay, so you can see right away that there's an interplay between place and value encodings of disparity. The correlation cells represent the tuned excitatory cells, and they, by follower aggregation, this is a place encoding, right? Okay, now by follower aggregation, you turn it into a value encoding of disparity. Now through the bump circuit, which is a little bit, if you look at the pieces of the bump circuit, a little bit like the near and far cells, by turning it, going from this value encoding of disparity, you can now use that to go back to a signal which feeds back into the place encoding of disparity. It's really cool. So that's done by this next step, which is winner-take-all competition. So you also have to have competition along each cyclopean pixel to make sure that there's only one match of features from the top and bottom retina. Okay, and you do that by taking the correlation value, feeding it into the winner-take-all. Remember, this is the collective correlation value, right, after the bump. You take that, and then you use that to inhibit every pixel, too. That kind of enforces uniqueness. Okay, so here is what that whole, I've turned off my video so you can see the circuit better. Here's what that whole stereo correlator cell looks like. It's really a beautiful thing. Let me explain what's going on here. So again, now already we had gone to spiking silicon retina. So the spikes from the top retina and the bottom retina would come in here as low going pulses. So whenever you spike at the same time, you get an AND circuit. Both of these guys are on. And so then that correlation signal, that very simple AND correlation signal, is mirrored into this node here. This is the input of the winner-take-all, right? But it's added together to this current here. This current is the mirrored output of the bump circuit. And the bump circuit input is coming from one input is coming from the analog valued unit. This is the analog value of the disparity at this cyclopean pixel. So that's coming into one input. The other input to the bump circuit, the other half of the input to the bump circuit, is this disparity reference analog voltage signal. And remember, that's added together to drive the correlation that feeds the winner-take-all. But the bias on this bump circuit, which weights how much you weight this similarity, is coming from the output of the winner-take-all circuit here. Then the winner-take-all circuit is mirrored out here by this mirror and then this mirror, and that goes into the bias, the follower. The follower again is taking the disparity reference. It's another one that's taking the disparity reference, and that's the input here. And then the output of this transconductance amplifier goes in. Let's see, the input to the follower is coming from the disparity reference, and the output of this follower is driving the disparity reference, and it's biased by the winner-take-all output here. Okay, this you can see right away that there's tons and tons of feedback and stuff going on in this pixel. I mean, I would challenge anybody to mathematically model it accurately with all the exponentials and nonlinearities happening here. But look at how much it's doing with only 21 transistors. I mean, it's really amazing. So, but that's not all. So now there's one more aspect of this, which came around about the same time, which was simulated by Ken Nakayama and Shin Shimojo's DaVinci stereopsis illusion. You can read about it here, DaVinci stereopsis. The fact that it's called DaVinci stereopsis suggests that it's Leonardo da Vinci, T.T. Liu's hero, the Renaissance polymath, came up with this idea. And can you see what it is here? So you have here a stereo pair. Again, if you zoom this back out and do a fusion on it, I think it's uncrossed again, uncrossed fusion of these two images, you'll see that there's actually a difference between the left and right images, just white dots on a black background. Do you see what the difference is? Here on the left image, you have these two white dots. You're right, you don't have them. On the other hand, on the right image, you have these two dots, and the left one doesn't have them. Right? So it's like there's features in each view that the other eye doesn't see. And what can cause that kind of stimulus? Well, this black triangle standing out in space could cause occlusion so that the left eye or the right eye doesn't see features. So the DaVinci demonstration, and what you see actually when you look at that is this a very strong impression of a black triangle with nothing on it, just floating out in space. And so this DaVinci demonstration showed the importance of unmatched features. Now, only the left eye sees this, only the right eye sees this, and that causes very powerful impression of something floating out in space. What does that mean, though? How do you bring that aspect of psychophysics and cortical neurophysiology into the chip? And that's done by so-called monocular cells. Those are cells that only respond to one input, one eye's input, and not the other eye's input. And so this suggested Misha's monocular cells, which I won't talk about anymore right now, but you can read about them in the paper. And what they do, what the big influence of these monocular cells is where you had an input from one eye and not the other eye, is it had an impact on the winner-take-all competition, and it would break, and in my recollection, it would actually break this fusion here, this smooth disparity. So it would have an influence directly, yeah, that's right. The monocular input would interact with the winner-take-all, and it would also serve to nonlinearly increase the resistance of this resistive network to allow this sudden jump in depth. It's really beautiful. I just think it's so lovely, all the interplay of different representations here. So you can see now that in Misha's stereo chip, she had analogs of the tuned excitatory cells, those are the correlation cells. She had the near and far cells, that was in the outputs of the bump circuit. She had the tuned inhibitory cells, that was in the monocular neurons that I just showed you, and she had disparity flat cells, that was somehow, I believe, in the analog value unit. And so I hope you enjoy this view at how it actually works. Oh, yeah, I didn't have it quite right, but anyway, you should read about it if you're more curious about it, because it definitely takes some time to sink in. Okay, so I'm going to now play you the video demonstration of Misha's stereo system demo, which you saw briefly Misha talking about in her in the Misha Prize Award. The idea was you had a left retina or a computer and a right retina and a computer, and you would just feed in corresponding rows of the retina, right? So the stereo chip only kind of did a 1D stereo problem on a 2D surface here, and then the output would go on by video scanner to a monitor. So now I'm going to play the video of Misha's demo. Apologies for the audio. I worked hard to try to clean it up. It's a bit belabored, but if you watch it a couple of times, you'll see the idea of Misha's stereo chip.
Chip receives input from a hardware interface to a standard digital workstation. The output of the chip is displayed on a video monitor and oscilloscope. The stimulus to the upper retinal input is elongated and the targets appear spread apart. The correct matches appear at various positions in the correlator array.
That's the analog disparity unit.
So the analog voltage output and the disparity unit on the oscilloscope.
The spikes are generated from the computer.
The inhibition level is constant over the stimulus array. When the positive feedback is turned off, false targets appear in the correlator array.
Misha has turned off the winner-take-all, so now the false matches appear.
All the possible targets. When the positive feedback is reinstated, false targets are suppressed, in the analog voltage outgoing retinas that image a blinking LED onto their surfaces. The blinking LED is visible in the outputs of the two retinas, which are displayed on the monitors here and here.
Here's an LED, a flashing LED that generates
When
spikes
one
in
of
the
the
two
retinas
retinas.
is occluded,
Two
by
retinas.
covering its lens, the target disappears from its output display.
It covers up one of the lenses here with her hand. This one disappears.
The
And now the
outputs of
stereo
these two
match.
retinas are transmitted to the stereo correspondence chip.
This one up here.
The output of the stereo correspondence chip is shown here. The bottom retina
This one.
goes to the bottom retina of the stereo correspondence chip. The top retina goes to the top retina. Forth across the visual field, the stereo correspondence chip continues to calculate the disparity of the target. If I move the target closer and farther from the two retinas, the disparity of the solution will change. If I move the target closer, the solution moves lower in the correlator array. If I move the target farther away, the solution moves back in the correlator array,
It moves down here, right?
indicating a change of depth.
You can see
This
the
change of
disparity
depth
here.
is also shown in the analog valued output on the top face of the oscilloscope.
That's right here. That's the analog
This is
disparity.
for far disparity, and this is for near disparities. When the disparity of the stimulus exceeds the fusional area of the stereo correspondence chip, the targets appear independently in the monocular cells of the array. Now it's too close, and now it's too far.
Not sure about that. Now they're lined up. You can see the disparity
The
matching.
stereo correspondence chip is able to the solution remains correct no matter where I put the additional target.
Now there's another LED here. Right, one's fixed and the other one is over here. You can see the
If I juxtapose the two targets so that they're at the same disparity but close to each other in the visual field, then there's a potential for formation of false matches between the two targets. If I turn the positive feedback of the correlator array off,
now
the
you should
false
see,
targets become visible.
see the false matches here?
The false targets are
There.
spread throughout the disparity space, but the average position of the false targets remains near to the correct solution.
This one.
When the positive feedback is reinstated, the correct solution once again appears in the array.
Which I think she's going to do now. Okay. That concludes the demonstration. And if you want to read more, like I say before, you can read it on Misha's PhD thesis online from my website. I have the whole PhD thesis. Also, there's a Kluwer book about Misha's thesis, very expensive Kluwer book, maybe online now available too. And there's a recent work inspired from these ideas from Mark Oswald, which is mostly a simulation study, but I did try to take the next step. I haven't covered at all what's happened in deep learning. I haven't covered at all what's happening in deep learning, but in these big CNNs that are trained on lots and lots of data, whether people have done it with video, with recurrent convolutional nets, whether these networks actually exhibit these classes of cells that you see in cortex. But I do hope you enjoyed this tour through Misha Mahowald's beautiful stereo chip. Goodbye.